Welcome! In this session, we'll be solving the problem number 1426, counting elements. This problem challenges us to think critically about array traversal and conditional checks. We'll explore a range of approaches and evaluate their efficiency. Let's dive in. In this problem, we are given an integer array called ARR and need to count how many elements in the array have the property that their value plus 1 also exists in the array. For example, if an element x is in the array, we check if x plus 1 is also in the array. If it is, we count that occurrence. Importantly, if there are duplicate values in the array, each occurrence is counted separately. The input will always be a list of integers, with its length ranging from 1 to 1000 and each element between -1000 and 1000. The output is a single integer representing the total count of elements that meet this condition. For instance, consider the example where the input array is 1, 2, 3. The output for this case is 2. This is because the elements 1 and 2 satisfy the condition, 1 plus 1 equals 2 exists in the array, and 2 plus 1 equals 3 also exists in the array. However, the element 3 does not satisfy the condition because 3 plus 1 equals 4 is not present in the array. So, the total count of elements meeting the condition is 2. Now, let's look at another example to understand how duplicates are handled. Consider the input array 1, 1, 2, 2. The output for this example is 4. Here's why: the first one satisfies the condition because 1 plus 1 equals 2 exists in the array, and the second one also satisfies the condition for the same reason. Similarly, both occurrences of 2 satisfy the condition because 2 plus 1 equals 3 exists in the array. Although the value 2 appears multiple times, each occurrence is counted separately if it satisfies the condition. This results in a total count of 4. Next, let's explore a more complex example with varied elements. Now, take the array 1, 3, 2, 3, 5, 0. The output is 3. Let's break it down. The elements 1, 2, and 0 satisfy the condition. Specifically, 1 plus 1 equals 2 exists in the array, 2 plus 1 equals 3 exists, and 0 plus 1 equals 1 exists. However, the elements 3 and 5 do not meet the condition because 3 plus 1 equals 4 and 5 plus 1 equals 6 are not present in the array. Therefore, the total count is 3. Now that we've seen a few examples, let's discuss the problem's constraints and some edge cases you might encounter. The constraints specify that the array length will always be between 1 and 1000, and the elements will range from -1000 to 1000. Here are some edge cases to consider. First, if the array is empty, there are no elements to count, so the output is 0. If the array contains only one element, such as 7, the output is also 0 because 7 plus 1 equals 8 does not exist in the array. In cases where all elements satisfy the condition, like 1, 2, 3, 4, the output is 3 because only the largest element, 4, lacks a 4 plus 1 value in the array. Lastly, negative numbers are valid inputs too. For example, in the array -2, -1, 0, the output is 2 since -2 plus 1 equals -1 and -1 plus 1 equals 0 both exist in the array. These edge cases ensure the problem is robust and covers various scenarios. To begin solving this problem, we can consider the brute force approach, which directly follows the problem's instructions. The idea is simple. For each element in the array, we check if its successor, x plus 1, is also present in the array. If it is, we increment a counter. To break this down, we first initialize a counter to 0. Then, we iterate over every element in the array. For each element, we use either a nested loop or Python's an operator to check if x plus 1 exists. If it does, we increment our counter and eventually return it as the result. However, while this approach is easy to understand and implement, it has a major drawback. Since we may end up scanning the entire array for each element, the time complexity grows quadratically, n squared. As a result, this method can become extremely slow for large input sizes. The key trade-off here is simplicity versus efficiency, and unfortunately, this approach does not scale well. Now, to address the inefficiencies of the brute force method, we can turn to an optimized approach that uses a hash set. A hash set allows us to check for the existence of an element in constant time on average, which drastically improves performance. Here's how it works. First, we pre-process the array by converting it into a hash set, which we'll call elements. This allows us to perform membership checks quickly. Next, we initialize a counter to 0 and iterate through each element in the original array. For each element, we check if x plus 1 exists in the hash set. If it does, we increment the counter. Finally, the counter is returned as the result. The key insight here is that by using a hash set, we eliminate the need to repeatedly scan the array. This reduces the time complexity to O(n), as we only iterate through the array once and perform constant time lookups. The space complexity is O(n) as well, due to the hash set. While this approach uses more memory, it's a worthwhile trade-off for the significant gain in efficiency. The optimized approach using a hash set is the strategy we chose, as it provides the best balance between time and space efficiency. The main insight was realizing that instead of repeatedly searching the array for x plus 1, we could pre-process the data into a hash set and perform efficient lookups. This reduces the time complexity from O(n) squared to O(n), making the solution far more scalable for larger inputs. One of the highlights of this approach is how simple it is to implement using Python's built-in data structures. The aha moment came when we recognized the power of set lookups compared to linear searches. By pre-processing the array into a hash set, we not only avoided redundant work but also ensured that the solution handles duplicate elements properly. Comparing the approaches, the brute force method is straightforward but impractical for large datasets due to its inefficiency, while the optimized approach achieves a dramatic improvement in speed with minimal added complexity. Although the hash set uses additional memory, the reduction in time complexity makes it the superior choice for solving this problem effectively. The problem asks us to count how many elements in the array satisfy the condition where x plus 1 is also present in the array. For instance, in the array 1, 2, 3, 4, the elements 1, 2, and 3 meet this criterion because 2, 3, and 4 respectively exist in the array. A straightforward way to solve this problem is the brute force approach. Here, we iterate through each element in the array and check if x plus 1 exists using a nested loop or a search operation. We initialize a counter to keep track of the satisfying elements, and for every x where x plus 1 is found, we increment the counter. Finally, we return the counter value as the result. While this approach is simple, repeatedly scanning the array for each element results in a time complexity of O(n) squared, in the worst case, which is inefficient for large arrays. A more efficient solution leverages a hash set to reduce the repetitive searches in the brute force approach. By converting the array into a hash set, we can perform membership checks in O(1) on average. The hash set provides a quick way to verify if x plus 1 exists without repeatedly scanning the array. We start by creating the hash set from the array, which stores all unique elements. Next, we iterate through the array, and for each element x, we check whether x plus 1 exists in the hash set. If it does, we increment our counter. Once all elements are processed, we return the counter as the result. This method significantly improves efficiency, as building the hash set takes O(n), and the iteration and lookup operations combined are also O(n). This gives us an overall time complexity of O(n). Key takeaways include avoiding the inefficiency of repeated searches by using a hash set and leveraging its constant time lookup for faster performance. This approach also handles edge cases effectively, such as empty arrays or arrays with duplicates, where the hash set automatically ensures each element is checked only once. The optimized algorithm also handles negative numbers and zeros seamlessly, as these values do not introduce any additional complexity when performing hash set lookups. In terms of data structures, we primarily use the input array for iteration and the hash set for efficient membership checks. To see this approach in action, here's a Python implementation. First, we create a hash set from the input array. Then, we initialize a counter to 0. As we iterate through the array, we check whether x plus 1 exists in the hash set for each element x. If it does, we increment the counter. Finally, we return the counter value. This code highlights the simplicity and efficiency of the optimized approach, with clear steps and minimal computational overhead. The use of the hash set ensures that our solution is both elegant and scalable. To deepen our understanding, let's walk through an example. Consider the array 1, 2, 3, 4. First, we create a hash set containing 1, 2, 3, 4. During iteration, for x equals 1, we check if 2 exists in the set, and it does, so we increment the counter to 1. For x equals 2, we check if 3 exists, and again it does, so the counter becomes 2. For x equals 3, we check if 4 exists, which it does, so the counter increases to 3. Finally, for x equals 4, we check if 5 exists, and since it doesn't, the counter remains 3. Therefore, the output for this input is 3. Now consider another input, 5, 1, 2, 3, 7, 6. The hash set becomes 1, 2, 3, 5, 6, 7. For x equals 5, 6 exists, so the counter is 1. For x equals 1, 2 exists, making the counter 2. For x equals 2, 3 exists, so the counter becomes 3. For x equals 3, 4 doesn't exist, so the counter remains 3. For x equals 7, 8 doesn't exist, keeping the counter at 3. Finally, for x equals 6, 7 exists, so the counter becomes 4. The result for this input is therefore 4. In conclusion, the optimized approach outputs count equals 4 for the second example. By using a hash set, we achieve significant efficiency improvements compared to the brute force method. This solution is not only faster but also handles edge cases and duplicates gracefully, making it a robust and scalable choice for the problem. The example walkthroughs illustrate how the algorithm processes each element, ensuring that all valid conditions are checked while avoiding unnecessary computations. This completes our deep dive into the algorithm, demonstrating both its theoretical foundation and practical application. This implementation solves the LeetCode problem number 1426, counting elements. The goal is to count how many elements in the input list ARR satisfy the condition x plus 1 is also present in the list. The code begins by converting the input list ARR into a set, named element_set. This is done because lookups in a set have O(1) time complexity, making it efficient to check for the presence of x plus 1. Without this conversion, checking for the presence of elements would require a linear search, leading to a less efficient O(n)² overall complexity. Next, the code initializes a variable count to 0. This variable will track the number of elements in ARR that meet the condition x plus 1 exists. The code then iterates through each number in the input list ARR using a for loop. For each number, the code checks whether number plus 1 exists in the set element_set. If the condition is true, the count variable is incremented by 1. Finally, after completing the iteration, the function returns the value of count, which represents the total number of elements satisfying the condition. This approach ensures an efficient solution with a time complexity of O(n), where n is the length of the input list. The space complexity is O(n), due to the usage of the set to store unique elements from the list. Overall, the code is concise, efficient, and handles all edge cases, such as an empty list or a list with no elements that satisfy the condition. This is the Java implementation of LeetCode problem number 1426, counting elements. The logic mirrors the provided Python implementation, using a hash set for efficient O(1) lookups to check if an element's successor exists in the array. The main differences in Java include type declarations, the use of the hashset class, and explicit iteration over arrays using a for each loop. The method iterates through the array, counts elements that have their successor present, and returns the result. Here, we start with the first example where the input array is 1, 2, 3. First, we initialize some variables. The input array is stored as ARR equals 1, 2, 3, and to make our lookups more efficient, we convert this array into a set, resulting in element_set equals 1, 2, 3. Using a set allows us to check for the existence of elements in constant time. We also initialize a variable count to 0, which will help us keep track of how many elements in the array satisfy the condition. Now, we begin iterating through the array. On the first iteration, when number is 1, we check if number plus 1, which is 2, exists in element_set. Since 2 is in the set, we increment count by 1, making it 1. On the second iteration, number is 2, and we check if number plus 1, which is 3, exists in the set. Again, 3 is found in the set, so we increment count to 2. On the third and final iteration, number is 3, and we check if number plus 1, which is 4, exists in the set. This time, 4 is not in the set, so count remains 2. Now that we've finished iterating through the array in example 1, the final value of count is 2, as there were two numbers in the array for which number plus 1 exists in the set. Therefore, the output for this example is 2. Moving on to the second example, the input array is 1, 1, 2, 2. Again, we begin by initializing our variables. The input array is stored as ARR equals 1, 1, 2, 2, and we convert it to a set to get element underscore set equals 1, 2. Note that even though the input array contains duplicate values, the set automatically removes duplicates, leaving us with just the unique values. We also initialize count to 0, as we'll use it to count how many elements satisfy the condition. In this example, we start iterating through the array. On the first iteration, number is 1. We check if number plus 1, which is 2, exists in element underscore set. Since 2 is in the set, we increment count to 1. On the second iteration, number is also 1 again. We perform the same check, and because 2 is still in the set, we increment count again, making it 2. On the third iteration, number is 2. We check if number plus 1, which is 3, exists in the set. This time, 3 is not in the set, so count remains 2. On the fourth and final iteration, number is 2 again. We repeat the same check, and since 3 is still not in the set, count stays at 2. After completing the iteration, we find that the final value of count is 2, and the output for this example is also 2. In the third example, the input array is 1, 3, 5, 7. Once again, we start by initializing our variables. The array is stored as ARR equals 1, 3, 5, 7, and converting it to a set gives us element underscore set equals 1, 3, 5, 7. We also initialize count to 0. Next, we begin iterating through the array. On the first iteration, number is 1. We check if number plus 1, which is 2, exists in element underscore set. Since 2 is not in the set, count remains 0. On the second iteration, number is 3. We check if number plus 1, which is 4, exists in the set. Again, 4 is not in the set, so count stays at 0. On the third iteration, number is 5. We check if number plus 1, which is 6, exists in the set. Since 6 is not in the set, count remains 0. Finally, on the fourth iteration, number is 7. We check if number plus 1, which is 8, exists in the set. Once again, 8 is not in the set, so count stays at 0. After iterating through the entire array in example 3, we see that there are no numbers for which number plus 1 exists in the set. As a result, the final value of count is 0. Therefore, the output for this example is 0. This demonstrates that when no elements satisfy the condition, the count remains 0, and the solution correctly outputs the result. Here, we analyze the time complexity of our solution by breaking it into two main steps. First, we convert the array into a hash set using the set ARR operation. This involves iterating through every element in the array, and since each insertion into the set has an average time complexity of O(1), processing all n elements takes O(n) time. Next, we iterate through the array with a for loop. For each element, we check if number plus 1 exists in the hash set. The lookup operation in a hash set is also O(1) on average, and since we perform this operation for all n elements, the total time complexity of this step is O(n). When we combine both steps, the overall time complexity becomes O(n) plus O(n), which simplifies to O(n). Now, let's look at how the time complexity holds across different scenarios. Whether it's the best case, average case, or worst case, the time complexity remains O(n), because the algorithm processes each element in the array exactly once and performs a single constant time lookup in the set for each element. Moving on to space complexity, we analyze the additional storage used. The hash set, element underscore set, stores the unique elements from the array. In the worst case scenario, where all elements are unique, the hash set will require O(n) space. Besides the hash set, the solution uses a few integer variables like count and number, which require only O(1) space. When we combine these factors, the total space complexity is O(n). Let's compare this optimized solution to a brute force approach. In the naive method, we would iterate through the array for each element and check if number plus 1 exists. This results in a nested loop with time complexity O n squared, which is significantly slower than the linear O n complexity of our optimized solution. By leveraging a hash set, we reduce the lookup operation for number plus 1 to O 1, allowing us to achieve a much more efficient linear time complexity. The trade-off here is the O n space required for the hash set, but this is a small price to pay compared to the performance gain. Finally, we confirm the big O analysis. With n elements in the input array, building the set takes O n time, and iterating through the array with constant time operations for each element also takes O n. This gives us a total time complexity of O n. The space complexity remains O n, because the hash set stores at most n unique elements. Overall, this solution strikes an excellent balance between time and space efficiency. Now, let's look at some common mistakes developers encounter with this type of problem. First, failing to account for duplicates can cause you to count the same pair multiple times, especially if you're iterating over the array without proper checks. To avoid this, consider using a set to keep track of processed elements or skip duplicates during iteration. Second, inefficient element lookup is another frequent pitfall. If you're using a list search, like checking if an element exists with X and ARR inside a loop, you're introducing O n squared time complexity, which is far too slow for large inputs. Using a hash set brings this down to O 1 for lookups. Next, be mindful of edge cases. For example, arrays that are empty or have only one element can lead to runtime errors if not explicitly handled. Additionally, don't forget about negative numbers. If your logic involves checking for something like x plus 1, you need to ensure it works for negative values as well. Finally, overcomplicating the solution is a trap to avoid. Introducing unnecessary complexity, such as sorting the array when a hash set suffices, can increase the runtime unnecessarily. Always aim for the simplest and most efficient solution possible. To succeed in interviews, it's important to develop specific insights and strategies. Recognizing patterns is crucial. Many problems revolve around relationships between consecutive or related elements. Identifying the need for fast lookups and leveraging tools like sets or dictionaries can save valuable time. You should also weigh the trade-offs between different approaches. For instance, while sorting is often a reliable technique with O n log n complexity, hash-based solutions with O n are generally faster and more suitable for performance-critical scenarios. Additionally, think about the balance between space and time. Using extra space, such as a set, can significantly improve time complexity, but it's always a good idea to clarify constraints with your interviewer to choose the best approach. Finally, maintain an optimization mindset. Start by quickly explaining the brute force approach to establish your understanding, then shift focus to optimizing the solution. This demonstrates both clarity of thought and problem-solving ability. It's also helpful to explore related problems to deepen your understanding. For example, LeetCode 128, longest consecutive sequence, is a classic problem that emphasizes the use of hash sets for optimal performance with consecutive integers. LeetCode 217 contains duplicate, focuses on efficiently checking for duplicates using sets. Another well-known problem is LeetCode 1.2 sum, where hash maps enable quick lookups to find pairs efficiently. Additionally, LeetCode 532, if pairs in an array, involves finding pairs with a specific difference, requiring thoughtful use of data structures. Now, when considering alternative approaches, sorting the array is one option. This allows you to iterate and count consecutive elements, but it comes with O n log n complexity, which is slower than hash-based methods for large inputs. The hash set approach, on the other hand, is typically more efficient. By storing elements in a set and checking for x plus 1, you achieve O n time complexity, albeit with O n space. For certain variations, you might also explore in-place modifications, such as marking visited indices. While this can save space, it often complicates the implementation and may not always be allowed during interviews. Carefully evaluate these trade-offs to select the best solution for your specific constraints. Great job! To summarize, we learned how to efficiently solve the counting elements problem using hash maps for optimal performance. Remember, understanding the trade-offs between different approaches is crucial. Thanks for joining, and see you in the next problem-solving session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!